In the previous lecture or in the yesterday's lecture, we basically derived or calculated the formulations for stresses in the case of thick cylinders by using the MOS theory. So we derived the formulation for hoop stresses, the radial stresses, and the longitudinal stresses. Today we are going to discuss how to determine the strains in the thick cylinders, and then we will solve some numerical problems where we will apply the formulations that we have derived yesterday and today. So to calculate the strain in case of thick cylinder, the concept is same. If you remember the thin cylinder, we have to apply the same concept and same formulation to determine the strains in the cylinder. For example, we are interested in calculating the change in diameter of thick cylinder. Now, if you remember, the change in diameter is caused by hoop stresses because they are acting perpendicular to the cross section or any section. So they will cause uh, the change in diameter or radius or circumference. So we know that change in diameter or the diametric strain is represented as change in original diameter. Now this diametric strain is equivalent to the hoop strain. But we also know one thing, that whenever the strain acts in the middle minor strains in two mutually perpendicular direction. So this diametric strain will then be equal to hoop strain minus mu into epsilon L. So if you remember that it is the same formula.
So your voice is continuously breaking.
Okay, give me a moment. Is it any better now?
Yes, sir. Yes, sir. It's good.
Okay. So I was talking about how can we determine the change in diameter in the case of thick cylinder. The concept is same as we applied in the case of thin cylinder. We know that the change in diameter is caused by the hoop stresses because they are acting perpendicular to the cross section. And if you remember that figure of the cylinder, the hoop stresses can cause the elongation of the radius or the diameter of cylinder. So we know that change in diameter or diametric strain is represented by change in diameter over original diameter. Now this diametric strain is equivalent to the hoop strain, or I can write it over here, that is equivalent to the hoop strain. So if I represent the hoop strain, if the strain occurs in one direction, it will produce some minor strain in two mutually perpendicular directions, which can cause the reduction in original strain. So that reduction is shown by these vectors. Now, if hoop strain is our original strain, it will produce small strain in the longitudinal direction, but the only difference between thin and thick cylinders over here is that in the case of thin cylinder, we neglected the radial strain. So the formulation was only this, epsilon h minus mu into epsilon n. But like we discussed yesterday, that in the case of thick cylinder, we cannot neglect the radial stresses, and similarly we cannot neglect the radial strains. So because their magnitude is comparable to the hoop stresses or the longitudinal stresses, so we have to consider this strain as well. So this is the formulation for the calculation of change in diameter, and if I simplify this one, I will get this epsilon h will be sigma h over e minus nu sigma L over E minus nu sigma R over E. So if I take this 1 over E as common, it will give me 1 over E sigma H minus nu sigma L minus nu sigma R. So this D will go on to the other side as well. So by using this simple formula, we can calculate the change in diameter in the case of thick cylinder if we know the hoop stresses, longitudinal stresses, the radial stresses, the original diameter, and modulus of elasticity, and this uh, Poisson's ratio. So this is how you calculate the change in diameter in the case of thick cylinder. Similarly, for the change in length, if you remember that the longitudinal strains or the stress in the longitudinal direction will cause the change in the length of cylindrical element, because they are acting somewhere like this one in the cross section. So either they will elongate the cross section or overall length of the section, or they will cause the decrease in the length of cross section. So they are responsible for the changes in the length. So we have to utilize this longitudinal strain to calculate the change in length. So how will we do that? We will apply the same procedure that change in length or original length is equal to strain in the longitudinal direction. But obviously when the strain is being produced in one direction, it will produce some minor strains in other two directions as well. So it will be equal to epsilon L minus nu into epsilon H minus the third direction is this radial direction. So if I simplify this one, again I will get 1 over E sigma L minus sigma H minus nu into sigma R. This length will go on to the other side, and this is our relationship for the calculation of change in length, provided that we know the longitudinal stress, hoop stresses, or the radial stresses. So these are two formulations for the calculation of strains in the thick cylindrical element. So now we will move on to the numerical problem related to these thick cylinder. Let us consider this problem. In this one, there is a thick cylindrical pipe of external diameter of 300 millimeter and internal diameter of 200 millimeter, and it is subjected to an internal fluid pressure of 20 megapascal and external pressure of 5 megapascal. And we need to determine the maximum hoop stresses that are developed and draw the variation of hoop stresses and radial stresses along the thickness as well. So there are two things. We have to calculate the hoop stresses or the maximum hoop stresses and the radial stresses. And we also need to show them on the cross section that how does it vary. For example, yesterday we were discussing that they would vary parabolically with respect to the thickness of the cylindrical element. Now we have to prove it as well in this question. And let's just start with this one. Okay, first thing that there are two ways to solve these kind of problem. One is this that we use these two formulations. In this formulation, if you look at that problem that I just showed you, we have been provided with the internal radius, internal pressure, external pressure, and the outer radius or inner radius. Similarly, we know all these factors, and only difference is this R factor. Now this R factor is the radius at a random point. So we have to substitute different values of radius into this factor to calculate the radial stresses, or similarly in this case, we have to substitute different values of radius to calculate the hoop stresses. For example, the cross section looks something like this one, and this is our center point. So this is the internal radius, and this over here is the external radius, right? So in between these two radius, there are numerous values of this R factor. For example, if I want to calculate the hoop stresses at this point, I will substitute R values equal to Ri. And if I want to calculate this, the hoop stresses at this point, for example, I will substitute the R value equal to from center to this distance. Or similarly, if I will keep on substituting the R values, and I will keep on getting the hoop stresses and the radial stresses at different points along the thickness of the cylinder. But again, it would be an inconvenient or hectic technique to do it for all the points, particularly in the case when you have to show the variation. So we will use the basic equations of Lamé's theory, which are these two equations, to calculate the radial stresses or hoop stresses at different point in this question. I'll show you how. So we have been provided with external diameter as 300 millimeter. So what will be the radius? And similarly, the internal diameter as 200 millimeter. So the internal radius is, what will be this value? This is 150, right? And this value over here is 100 millimeter. Also, the internal pressure is given as 20 megapascal, and the external pressure is given as 5 megapascal. And we need to figure out the maximum hoop stresses, the maximum radial stresses, and also we need to find out the variation or to calculate the hoop and radial stresses at different points. So our original equation, or the original Lamé's equation, was something like this one. Sigma R is equal to A minus B over R square. By the way, can any one of you tell me that what is the radial stresses in this question? Anyone?
Sir, PI complete कर लेना minus लगा दे.
So at the internal radius, the radial stresses are already given, that is 20 megapascal. And similarly, at the external radius, it is also given as 5 megapascal. So we need to determine the values of radial stresses in between to show the variation. So again, we will apply the boundary condition to figure out the values of these two constants A and B. So let us apply this boundary condition. The first condition is that at R is equal to 100 millimeter, sigma R is equal to minus 20 megapascal. And similarly, at R is equal to 150 millimeter, sigma R is equal to minus 5 megapascal, right? So I will substitute these two values into this equation, and I will get two simultaneous equations that are minus 20 is equal to A minus B over 100 square, that is equation 1. And the second equation is minus 5 is equal to A minus B over 150 square. So if I solve these two equations simultaneously, I will get the values of A and B. Now you have 2 minutes, just calculate the values of A and B and give me the answers. So what is the value of A? Anyone? Daniel.
Sir, 0.27. B. B
B
is
is
0.27.
0.27. Can anyone else compare these values?
So 2.16 into 10 to the power minus 3. B.
2.16 into
10 to the power minus 3.
10 to the power minus 3. So either I have the wrong answers or maybe you are making some mistake.
Sir, B की value 270 exponent 3.
What is the value?
270 exponent 3.
Yes. Can anyone else compare this? So the value of B is 270,000. 3 zeros. So what is the value of A now?
Sir, 7.
The value of A is 7, yes. So these are the two answers. You can check your calculations. So you will get these answers. So if I substitute these values back into the equation of radial stresses, can you please turn off your mic? So if I substitute these values back into the equation of radial stresses, I will get sigma r is equal to 7 minus 270,000 over r square. And similarly, the equation for hoop stresses was A plus B over r square. So hoop stress will be 7 plus 270,000 over r square. Now we have the equation for radial stresses and hoop stresses in the form of this radius or the random radius from the center or random distance from the center point. So if I keep on substituting the values of this radius, I will keep on getting the hoop stresses and radial stresses at different points on this radial element or this cylindrical element. So let us start with internal point first, that what are the hoop stresses and radial stresses at a radius of. Now keep your calculators with you and keep on giving me the answers quickly. So let's say first point we take that at a distance of r is equal to 100 meter or 100 millimeters. What is the value of radial stress and the value of hoop stress? Class, is it that difficult? You simply have to apply this formulation.
It's a minus 20 sigma r.
So if you please turn off your mic. So if you look at this value, you will see that this value is exactly the same as the internal pressure that is already given in this question, that internal pressure is 20 megapascal. So we calculated the radial stresses at internal radius and we have got exactly same answer with an opposite sign that is equal to our radial stress. So now what is the value of hoop stress?
So 34.
34 megapascal. So let us calculate the values at radius of 120 millimeter. So what is the radial stress at this point, and what is the hoop stress?
Say 11.75 minus 11.75.
Minus 11.75 megapascal, and the hoop stress is
So 25.75.
25.7 megapascal. So at R is because it was asked in the question that you should at least have 4 points to plot the variation. So we will take these 4 distances. Let's calculate this value at 135 millimeter. So what is the radial stress and what is the hoop stress?
So minus 7.8. So 21.8.
So what is the hoop stress at this 150 millimeter, or exactly at the outer radius of this cylinder? So only one student is solving the question. What are other students doing? I see there are 20 students at least in the class. Daniel,
Yes, sir. Yes, sir.
what are the values of this radial and hoop stresses?
सर मैं कर रहा हूँ मैं एक मिनट
Are you looking for your calculator now?
-5 hoops radial stresses.
-5.
Hoop stress is 19.
19 megapascal. So now we have different values of radial and hoop stresses at different points along the thickness of cylinders. So the next thing is we have to plot the variation. So how we are going to do that? Let's say that this is the cylindrical element with this thickness T. And since we have calculated this radial and hoop stresses at different points along this radius, this external radius is given as 150 millimeter, and this internal radius is given as 100 millimeter, and the value of hoop stress at the internal radius was 34 megapascal, and then the values continues to decrease. So if you look onto this diagram, this value over here is 34 megapascal and the final value was 19 megapascal. So this is how you represent the variation of hoop stresses along the thickness of the cylinder. And the maximum value of hoop stress was 34 megapascal at a radius of 100 millimeters. And the minimum value is 19 megapascal at a radius of 150 millimeters. So as we keep on moving from the center point to the external radius, the hoop stress will continue to decrease. And for the radial stresses, obviously we can't show it on the radius of the cylinder because it would be inconvenient. So we will represent this radial stresses in a similar way also on the other side of this cylindrical element. So let us show the radial stresses over this side. So the value was 20 megapascal at the internal radius, and then it continues to decrease and the final value was 5 megapascal. So if I connect these points, I will get the parabolic distribution for both these hoop stresses and this radial stresses. And the maximum value of radial stress is 20 megapascal at R is equal to 100 millimeter. So this is how you represent the variation of these hoop stresses and radial stresses along the thickness of the cylinder. So if there is any question about this numerical, you can ask me right now. If not, we can move on to the next one. Another thing that I have shown these stresses or these arrows in the upward direction because hoop stresses are acting or are the tensile stresses. You see with the sign, if it is negative, it means that they are the compressive stresses. So just to differentiate between the two values, these arrows have been shown or the tensile arrows have been shown towards the outside or away from the point, and the compressive stresses are shown moving inwards the radius of the element, just to differentiate between the two values so you can get an idea.
This
So
is
if,
possible then in a set of values, such in the cases of radial stresses, some values are negative and some are positive.
no, it won't be possible. Radial stresses are usually the compressive stresses, so they are exactly opposite to our internal pressure because it can't happen that the fluid stop exerting pressure on the walls and start to exert pressure towards the center of the. This is physically not valid. For example, whenever there is a fluid in a cylinder, let's say this is the cylinder and it has a fluid. So always it will exert the pressure on the walls of the cylinder, right? It can't happen that this will start exerting pressure on the center of the circle. So physically it is not valid. And the radial stresses are because of this pressure of the fluid. So they will be always compressive. So let us do another simple numerical. And hoop stresses are usually always tensile as well. In this question, we have been provided with the hoop and radial stresses at the inner edge of a cylindrical shell are 81 megapascal tensile. So hoop stresses are obviously tensile and the radial stresses as 40 megapascal compressive. The internal diameter of the cylinder is 180 millimeter and the length is 1.5 meters. And the longitudinal stresses are 21.93 megapascal. We need to find out the change in internal diameter, the change in length, and we have been provided with the modulus of elasticity as 200 gigapascal and Poisson's ratio as 0.3. Let us start solving this one. So the radial or hoop stresses were 81.88 megapascal. The radial stress is 40 megapascal, or I would put in the negative sign with this one. And the longitudinal stresses were 21.93 megapascal. The internal diameter is 180 millimeter and length is 1.5 meter. Length is 1.5 meter or 1500 millimeters. And E is given as 200 gigapascal or 200,000 megapascal, and mu is 0.3. And we need to find out the change in diameter and the change in length. So you need to keep one thing in mind that, for example, our equation for diameter or change in diameter was 1 over E sigma h minus nu sigma L minus nu sigma R multiplied by original diameter. So you need to keep or one thing in mind, or remember one thing, that in this question obviously we have been provided the internal diameter, and also these stresses are provided on the internal face of the cylinder. For example, if you see in this question that the hoop and radius stresses are provided at the inner edge of the cylindrical shell, but it can happen that in some cases you will be provided the hoop stresses, or you are not provided the hoop stresses at all, and you will be asked to calculate the change in diameter or change in the external diameter. So in that case you have to find out the hoop stresses or radial stresses at that point or at that radius, and then you need to know the original radius, and then you can use this equation to calculate the change in diameter. So for example, if you want to calculate the change in the internal diameter, you have to use these values for the internal diameter. And if there is any random diameter somewhere in between, you have to use these three values for that random radius or diameter. So let us solve this one. What will be the value of change in diameter? You have all the factors given in the question. So what is the value of change in diameter?
Sir, 0.07.
Is it 0.0785 millimeters?
Yes, sir.
So this is the change in internal diameter of the thick cylinder when these three stresses are acting on the cylindrical element. Similarly, the values of change in length minus nu into sigma h minus nu into sigma r into original length. So what will be the value of change in length?
Sir, 8.42 raised to the power minus 3.
8.42. Can anyone else confirm this answer? Can anyone else confirm this answer?
minus 0.109.
So I think the answer is 0.070. You simply have to substitute these values. E is 200,000, sigma L is 21.93 minus 0.3 into 81.88 minus 0.3 into minus 40, and the length is 1500. So if you calculate this, I have just calculated, the final answer is this 0.070. So you can check your answer. So is there any question about this numerical? Because these are the two things and it was a simple case. So in the case of cylinders, you are going to get similar type of questions. If you know how to use the formulations, obviously you can be asked to calculate the radius of the cylinder provided the stresses or the length of the cylinder. So the whole story will revolve around these 5 or 6 formulation, both in the cases of thick cylinder or in the case of thin cylinder as well. So try to review the whole topic, and if you have any questions, you can ask me. So this basically concludes our topic of thick and thin cylinders. And now we will move on to our next topic, which is
Sir,
eccentric column. Yes.
so where we want to find the stresses. Radius is given. We put those stresses at that radius in this
Yes.
system.
Yes.
Internal radius is given. We put dash stresses. If
Yes.
other point is given to us, then we put those stresses at that point.
Yes. We will calculate the stresses at that point, and then we will substitute into these equations. Okay.
Okay.
Is
Yes,
it
sir.
clear?
Yes, sir.
So, any other questions?
बट सर उसके लिए ए और बी की वैल्यूज अलग होंगी फिर?
Obviously, it depends. You can't be given directly these values of hoop stresses and radial stresses. Let's suppose the question may be something like this one. In this question, you can calculate the stresses at any radius. So maybe it can be asked in this question to calculate the change in diameter at this point, right?
बट सर हमें फिर बाउंड्री कंडीशंस भी चाहिए ना, लाइक फॉर डिफरेंट रेंज. जैसे हमने वो 4 पॉइंट्स के लिए सिर्फ एक रेंज सेट की थी और उसके लिए हमने बाउंड्री कंडीशंस रखे थे, तो इस वजह से ए और बी की वैल्यूज हम लोग 4 वैल्यूज के लिए सेम यूज़ कर रहे थे. तो
No, for example, in this question, this first question that we did, for example, let's suppose that it is the same question that have been provided to you again. And in this question, it has been asked to calculate the change in, let's suppose, external diameter. Okay. So what will you do? You will calculate the stresses by doing the same procedure for the external diameter, and you will have some stresses. For example, we had 34 megapascal as hoop stress and radius stress something like this one. So using these values, you will calculate the change in diameter of the change in external diameter, because you already know the external radius as well. So it is you can't do that in this question, because in this question you have been provided the stresses, but there isn't enough information to calculate or to figure out the values of stresses at different radius. But in this question or in the numerical one, you can do that. I am not
Okay.
sure about your question of boundary condition, because, for example, in this question, the boundary condition are same. They will remain same. How will it change?
फॉर एग्जांपल सर, अगर हमें चेंज इन डायमीटर एक रेडियस पे निकालना है जो इंटरनल रेडियस में है, लाइक एट अ
Okay.
पॉइंट व्हिच इज ऑन द इंटरनल रेडियस, सो उसके लिए फिर हमने ए और बी जो हम लोग निकालेंगे, तो उसकी बाउंड्री कंडीशंस हम क्या रखेंगे? दैट्स व्हाट आई एम आस्किंग.
No, the boundary conditions will remain same, because boundary conditions we select based on the, for example, let's say where are they, that at r is equal to 100 millimeter, sigma r is -20. So that is true for all the cases. So based on these boundary conditions, we have developed these equations. And you are asking that if we want to calculate the at the internal radius, we simply will pick up these values, or the values that we have calculated for r is equal to 100 millimeter. So there is no change in the boundary condition. You will use the same boundary condition or the same concept, but you will select these two values, that is 34 megapascal or -20 megapascal. Similarly, if you want to calculate the change in diameter or radius for at 120 millimeter or this radius, you will use these values of sigma r and sigma h. So you will move on like this one.
Okay, I
Right?
got it.
Okay. Is there any other questions? So if
Sir?
not, we yes.
सर आपने थिन सिलेंडर के लिए चेंज इन वॉल्यूम का भी फार्मूला ड्राइव करवाया था, थिक सिलेंडर्स के लिए चेंज इन वॉल्यूम क्यों नहीं हमने कंसीडर किया?
If you want, we can do that. Actually, the issue is that in the case of thick cylinder, the change in volume of that formulation gets very, very complex because there are numerous factors. You have to consider the thickness or the radius. So even in the literature, you won't find the change in volume for the thick cylinders at this stage. Maybe in some other degree you will find those formulations. So even in the literature you won't find that because it gets very complex.
ये न्यूमेरिकल 2 सामने करें थोड़ा
Yes.
सर इसमें अगर हमारे पास हूप स्ट्रेस नहीं गिवन होता और इंटरनल
Yes.
डायमीटर गिवन है तो हम ए और बी आप इस पे कैसे कैलकुलेट करेंगे?
That's what I am saying, that we can't calculate A and B in this question because we have been provided with the stresses directly.
लेकिन सर अगर हूप स्ट्रेस नहीं गिवन होता और सिर्फ इंटरनल डायमीटर गिवन है 180 मिलीमीटर तो हम खुद से
Okay.
बाउंड्री कंडीशन बना सकते हैं?
In this question we can't because we don't know the internal or external pressure. For boundary condition we do need to have some values of obviously we know the internal pressure, that is 40 megapascal at R is equal to, let's say, 90 millimeter. But what about external pressure? So there are two things. Either you take the external pressure as zero, which you can do in some questions, but again, we don't have to do the assumptions. It should be given in the question that the external pressure is zero, and also we have not been provided with external radius. So it should be told in the question. That's why I'm saying that we can't do that in this question. Right?
यस सर.
Okay. So I was thinking to start the next topic, but since we don't have enough time, so we will start this topic in the next class for this column. So this concludes today's class, and later on try to review all the derivations and all the numericals, and I will also give you a small assignment problem for these thick and thin cylinder. It won't have many problems, like 5 or 6 problems, but try to solve them. And if you have any questions, you can ask me. If not, this class is concluded. And also, can you tell me that have you done the or at which in the mechanics of solid course? Hold on.